Hello, this video is going to explain a number of MIPS programs illustrating bitwise logical operations in MIPS. For example, AND, bitwise OR, bitwise exclusive OR, bitwise negation, bitwise shift right logical, and shift left logical. And also, it's going to show you some MIPS programs, or some programs, I should say, in MIPS assembly language that illustrate how to convert a C for loop or a C if a statement to MIPS using unconditional jump instruction, which is J, or conditional jump instructions like branch equal, branch not equal, and also a few other instructions like SLT or SLTI, which stands for set on less than, immediate, for comparing two integers. All right, so let's go over what's going to happen in this program. Right now, I'm going to show you the very first experiment. Then after that, I'm going to change the program a little bit and show you the second experiment, change it a little bit and show you the third experiment by running them using an online service which basically simulates MIPS for you, so that you can test any programs that you write in MIPS without having to install anything on your own computer. All right. So let's see the first experiment. At the beginning, I'm going to begin my program using this statement. This is a system call for printing something on the output. What am I going to print? I'm going to print the ASCII string prompt. Where is it defined? If you scroll down all the way in the data section of the program, you will see the ASCII code prompt, which says, this program tests different MIPS arithmetic and logical operations, and then a new line, and then it says enter a non-negative number less than 100. The reason I use this statement is because I don't want the input to be very large. Numbers less than 100 would be reasonable, so it's going to be a two-digit or one-digit integer, then after it prints this on the screen or on the output stream, it's going to wait for the user to enter an integer, and that integer will be used later to do some arithmetic operation on it or logical operation on it. In this case, I'm going to do another system call, which is required to receive something from input, from the keyboard, let's say. I'm going to get that number and store it to V0 using the system call. Then I'm going to move V0 to S0, which is going to be the placeholder of N, which is the input for all the experiments that I show in this video. So I move N to S0 this way. Instead of using move instruction, you can use a normal add instruction and add V0 by 0 register, which is always 0, and store it in S0. Adding by 0 is neutral, so it basically means you're moving V0 to S0. So to summarize, so far all I did was I asked the user to enter some value, and I stored that value in S0. What do I do next? I'm going to do some illustrating instruction to show you how arithmetic operation and bitwise operations work in MIPS. So what I do is I simply say, let's AND or bitwise AND my N, my input parameter, with 23, which is a constant, and I store the result in S7. S7, which is the last saved register in MIPS, is always the placeholder of the output. Always I use S7 as the output in the rest of this video. So I use this instruction. It's called AND I. I means immediate, and I means end. some register with a constant. If you have both operands as registers, you can do the normal AND without the I. But if you want to AND, let's say S0 with a constant like 23, then do what I did. It means AND immediate by constant 23, and I store the result in S7. After this line, the remaining lines are all comments. I'll get back to these and I'll uncomment them to show you other experiments. So don't worry about that. Let's skip all of these and get to how to print the output. To print the output, I'm going to print a very nice informative statement. I will basically print the result 1 string, which is basically an ASCII string defined here. It says 23 and then after that, I'm going to print the value of n, which is in S0. And then basically this reads as 23 and n. Then I print is equal to, and then I print the answer, which was in S7. And it's going to print 23 and S0, and it's going to print the output on the, it's going to print 23 and whatever the input is, and then it's going to say is equal to the output. At the end, I'm going to print a new line, and it's going to end my program. To end my program, I use another system call. So whenever you see a system call, it's either because of an input operation or an output operation, or it's because I'm going to terminate this program like in the last 2 lines of the program, lines 109 and 110. This is the end of my text section, which is or text segment, which is basically the end of the block of memory containing the instructions. Then after that, you can just have more blocks of memory or more data. Let's say, as you see here, I have stored all the strings here at the end. So what I'm going to do is I'm going to run this program for an input n equal to, let's say, 10, and I'm going to observe the output. So before I do that, let's predict what's going to be the output if the input is equal to 10. So let's do some annotations here. What I'm going to do is very simple. I'm going to write down the bitwise end of 23 and 10 by hand, and I'm going to do it by hand and see what the result will be. Assuming that n is going to be 10, we're going to have 10, which is in binary, it's going to be a bunch of zeros, which I don't write, and then it's going to be 1 0 1 0. I don't write the leading zeros because I'm going to do the AND operation, and ending any number with 0 or any bit with 0 would be 0. So I don't care about that part. The bitwise end of the 10 and 23 will be equal to what? Let's do them digit by digit from the rightmost digit. What is the end of 0 and 1? Well, you may say, well, AND is a logical operation. What do you mean by ending 2 digits, 0 and 1? The answer is, just to explain what I mean, I should say 0 always represents false and 1 represents true, and then you can just do a normal logical operation between false and true. So false and true would be false, so this should be 0. The second rightmost digit would be and 1 and 1, which is equal to true and true is true, so it's going to be 1, true. So the next one would be 0 and 1, which is 0. The next one would be 1 and 0, which is 0, and the rest are going to be all zeros because the first operand 10 has all leading zeros except the last 4 digits. So the output would be this, which is a binary representation of number 2. If everything goes well, I should see 2 at the output if I give him input the value of 10. Let's see if we are right. So now it's time to test the program and see if it works properly or not. What I'm going to do is I'm going to switch to the Google Chrome where I have loaded this URL. This is basically an online MIPS simulator and assembler. And all I need to do is just browse my file system, look for the file that I was working on, the example.asm, and then I press open. And there you go. This is the program. You can see, for example, here I printed 23 and n is equal to the answer. So this is basically, the green part is my code, and in the left side you can see the canonical, or the I should say the standard version of what you write by converting all the registers to basically $0 to $31, and it's the standard form. You don't need to read the left side, only read the green part. The green part is what you wrote. And right now my PC is on this line, which basically means I'm going to start the program, right? PC means program counter. It's a register. All the special registers are going to be available here. And we have all the 32 registers of MIPS available here. You can view them while this program is running. And also you can do lots of things with this tool. You can either run the program all the way, or you can do step-by-step execution. That's perfect for debugging, especially because you have access to all the registers. You can view them here. So it's a very good online tool. So again, I use the browse button to load my program in this, and then I'm going to press play. Let's see, press play. The first thing pops up is this. This one is asking for the input. If you remember, I did a system call to ask the user for the value of n. Here I will place 10. And as I said again, if everything works properly, I should see 2 on the output. And before I press OK, look at this. This is the output that has been printed so far. It says this program tests different MIPS arithmetic and logical operations, enter a negative number less than 100. So this small window shows the output, and the input should be given the program this way if you're using Google Chrome like me. And I'm going to press OK, and it has stopped here, I guess, because I didn't run it quickly. Let's reload this. Let's reload the example again and press play. It says enter the number. I will say 10, and I press OK. And there you go. 23 and 10 is equal to 2. So that's the output, right? That's what we expect. With that first experiment finished, I'm going to go over the second experiment. The second experiment basically is quite similar. I'm going to test how to do an OR operation. So let's comment the AND operation and uncomment the OR operation. This is again OR immediate. I'm going to OR the input, which is stored in S0, just like the previous experiment, by 18 this time. I'm going to use a different constant, and we're going to see the output in S7. And at the end, when it comes to printing the output, I'm going to comment this line and uncomment this line, which brings result 2. Result 2 basically is a statement saying 18, or whatever the n is, which is going to be printed here, is going to be equal to, and then it's going to print the answer. So let's save everything, go back to the Google Chrome, browse the same file because I updated the same file, and I'm going to press play. This time I'm going to make it a little bit faster. You can change this execution speed this way by moving this scroll bar left and right. And then it's time to press play. It says input, I will say 10 again, and then it's going to print 18 or 10 for me. This time I'm going to show you how why this is correct, not by doing the OR operation by hand, because that would be boring. Instead, I'm going to use the Windows calculator. So this is the Windows calculator. I will do 23, and then I will do bitwise OR, and then I will do, well, this time it's n is not 23, it's 18. So it's going to be 18 bitwise OR 10, and then I press enter. The answer is 26. That's exactly what shows on the output of our MIPS assembly. The next operation, the next experiment is to do a bitwise. Let me bring it. It's bitwise XOR. So the third experiment is a bitwise XOR operation. And to run this, what I'm going to do is I'm going to comment the OR out, uncomment the XOR for the third experiment, and then I'm going to do similar changes that I did before. So I'm going to comment this out, uncomment this. This time I'm going to do an XOR between n and 9. So again, as you see, the instruction I'm going to use here is XOR I, which basically means let's do an immediate XOR, a constant XOR, which means XORing a register with a constant. All right, register is S0, constant in 9. See what the output will be. Let's go back to the Google Chrome, browse the same file, and press play. This time I'm going to use the same exact number, 10, and the output of 9 XOR 10 should be 3, based on what this line says. In order to test it, what I'm going to do is I'm going to open the calculator again, and here I will say 9 bitwise XOR 10, and the output should be 3. That's just how it is. For those of you who are wondering, like, what kind of calculator is this? Basically, you can use different modes of the calculator that Windows 10 or 11 has. I guess this is Windows 11. So you can pick like different modes. The standard mode is this one. The scientific mode is this one. And then if you go to the programmer mode, you can do lots of bitwise operations, shift operation, and all of that. So I tested this and it works properly. Let's go back. Now I'm going to show you the next experiment, fourth experiment, which is the bitwise negation. So let's uncomment the bitwise negation. I commented out the exclusive OR for the previous experiment, and now I'm going to do bitwise negation. In MIPS, there is no bitwise negation. If you want a bitwise negation, do a bitwise negation of a register, you gotta NOR it with 0. NOR means negation of OR. When you OR any register with 0, that's a neutral operation. You get the same exact register. But when you NOR it, that means you're gonna negate it, because OR with 0 is neutral, but NOR with 0 would be basically negating every single bit, which basically means 0 becomes 1, 1 becomes 0. So you're toggling every single bit of the 32-bit register that you have. In this case, my input is n in S0, the output will be stored in S7. This is basically the ones complement of n. So let's say if n is 10, what I expect on the output should be -11, because that's the bitwise, that's the numerical value of ones complement. Why the ones complement of 10 is -11? Because the twos complement, which is the negation of 10, which is -10, should be ones complement plus 1. That's how you get the twos complement. Ones complement plus 1. So when the ones complement is -11, added by 1, you get -10, which is the twos complement of 10. Twos complement of 10 should be -10. That makes sense. So what I'm expecting here is I should see -11 as the output if the input or S0 is 10. In order to print the output, I should do a few adjustments here. Let's uncomment this and comment line 84. Let's save this and let's try again. Again, I'm going to browse the same file and I'm going to press play, asking for the input 10, and then it says bitwise negation of 10 is -11, which is correct. That's what we expected. That's the ones complement. When you add the -11 by 1, you get -10, which is the two's complement of 10. The next experiment is, let's uncomment this next line, and let's do this. The next experiment is adding by 57. So whatever the input is, I'm going to add by 57 and I'm going to print it on the output. I means immediate, add I means add the constant. So let's see if we can see the expected output. Browse the same text file and then press play. I'm going to add 57 by 10 and the output should be 67. Let's see if that's the case. This is correct. So we are successfully finished this experiment. The next experiment is this one. I'm going to do 57 minus n. And this one would be a little bit more complex. Why is it more complex? I'll tell you why. We don't have a constant minus a register in MIPS. We do have add immediate and we do have a sub instruction in MIPS, but sub subtracts two different registers. Here I'm going to subtract a register from a constant. So what I'm going to do is I'm going to, instead of doing 57 minus n, I will do minus n plus 57. If you do a little bit of simplification, this would be equivalent to 57 minus n. So what I'm going to do is I'm going to first find the two's complement of n, which is -n. Then I'm going to add it by 57 to get the value that I'm looking for, which is 57 minus n. In order to do that, I need to first get the ones complement of n, which is bitwise negation of n, which means noting n, which is in S0 by 0. Noting with 0 gives you the bitwise complement or ones complement. Let's just store it in a temporary register T0. That's an intermediate result. That's not the final result. So it's better to store it in a temporary register like T0. Next line is adding T0 by 1 to convert ones complement to two's complement of n. Now T0 should contain -n. And finally, I'm going to add -n by 57 using add immediate and store the result in S7. So let's uncomment these three lines and do a little bit of adjustment at the output print. Let's save this. And what I'm going to do is I'm going to run the program. So let's go back to the browser. Let's browse same file, play. And this time I'm going to do 57 minus 10. The output should be 47. So that is correct. We did the correct code. The next experiment is, here's the next experiment. I'm going to find the sum of numbers from 1 to n. This is a very good example of how to convert a for loop in a higher level language like C into MIPS instruction. It's a very simple operation. I'm going to explain it to you. In order to get the sum of numbers from 1 to n, if you want to do it in C or C++ or Java or C# or any similar language, what you need to do is you need to define or declare integer sum, let's say, initialize it to 0, and then in a for loop for I from 1 to n, you need to add sum by I and then store it back to the sum. And at the end, sum will have the value that you're looking for. So I'm going to translate these two statements, the declaration of sum and also this for loop, to a MIPS instruction, to a MIPS code snippet, or to a MIPS sequence of instructions. So in order to do that, let's first comment out the previous experiment code. I want to deal with both of them at the same time. And I'm going to uncomment these lines, which is going to do the for loop for us. I'm going to tell you how this for loop can be managed. First, I'm going to declare a variable sum. I'm going to store sum in S7 because that's going to be the eventual output. So if the S7 represents sum, always that's how you need to do it. Every variable in a high-level language should be stored in a, let's say, a saved register, unless you don't have enough room. Then you can think of doing something else, like storing them in the stack or some other complicated things. But here we have very simple code. We have only 3 variables: n, which is in S0, sum, which is going to be in S7 because that's going to be the output. And we said at the beginning of the video that we're going to store always the output in S7. And also I have a counter I, which I'm going to store it in S1. I have many other save registers unused, so we are good in this case. Initializing sum to 0 looks like this. You just need to say, let's add 0 by 0. The answer is 0, and that's going to be the value of S7 or sum. And then we're going to start the for loop in a second. This is how you initialize the counter of the for loop. Basically, you say, let's add immediate S1, which is going to be a register representing variable I, S1, 0, and 1. So when you say add I, S1, 0, and 1, it means that let's add 1 and 0, store the result in S1. So that's how you initialize I to 1. Then after that, I'm going to have the rest of my for loop, which is going to be labeled as for 1. The reason I labeled this line is because I'm going to keep jumping back to this line because the for loop has to run multiple iterations. So you need to have a label right here. And then the first thing you need to do in your for loop is this condition check. You want to check whether the continuation condition is true or false. If it is true, you're going to keep going and do the next iteration. If it's not, you're going to get out of the for loop immediately. So in order to check whether I is less than or equal to n or not, I will do a SLT. SLT stands for set on less than, and basically it compares two registers as two signed integers. If you want to use unsigned version, you can use SLTU. It's an unsigned version, but we don't care about that one for now. So what I need to do is I'm going to say, let's compare S0 and S1. S0 is n, S1 is I. And I say if n is less than I, if S0 is less than S1, then set T0, which is a temporary register, equal to 1. Right? That's how you do the comparison. And then later after that, right after that, we have a branch not equal for T0 to see if T0 is set to 1 or not. If S0 is less than S1, which means if n is less than I, then T0 will be 1. Otherwise, T0 will be 0. That's why we call this set on less than, because if it's less, you're going to set the first register to 1. Otherwise, we're going to reset it, which means set it to 0. So it's going to set T0 to 0 if I is less than or equal to n. What does it mean? It means that if the continuation condition of the for loop is true, T0 will be 0. But if it is false, T0 will be 1. So when should I jump out of the for loop? When I is greater than n or n is less than I, which means if T0 is 1. So that's exactly what I do in the next instruction. I say, is T0, which is the result of comparison, is not equal to 0. If it's not equal to 0, that means it was 1, because we only have two values, 0 or 1. And if it is 1, we're going to jump to the exit 1, which is the end of this whole code snippet. We're going to end this completely, and then the output will be on S7, and then we're going to print it like the previous statement, previous experiments. But if you don't jump, that means if T0 is 0, so everything is fine, we still have more iterations for the for loop. Let's do the body of the for loop. What does the body of the for loop do? It's going to only add sum by I. Sum is in S7. We're going to add it by S1 using the add instruction, and we're going to store the result in S7 again. And then finally, as you all know, when you want to do the next iteration of every for loop, you need to update the counter. So we're going to do an I++ this way using add immediate. I'm going to add immediate S1 by 1 and store it back to S1. And then I'm going to jump to for 1, which is basically the beginning of the for loop. Of course, I'm not going to jump to this because this is going to initialize the counter back to 1. That should happen only once in the lifetime of a for loop. So the for loop will basically goes through these instructions multiple times until it gets out and gets into the exit. When it gets to the exit, we're going to go to the output statements, which is going to be here. We're going to print basically sum of numbers from 1 to n, whatever n is equal to, and then we're going to print the answer. So let me save this and go back to the Google Chrome, browse this same file, and then press play. What's the input? I will say 10, and it's going to do the calculation for me. The sum of numbers from 1 to 10 is 55. That's correct. You can verify the answer yourself. The next experiment is, let me comment these out. Okay. All right. So the next experiment is similar to the previous experiment, is basically sum of odd numbers from 1 to n. And to do this, not only I need a for loop, I need an if statement inside that, because if a number is even, I should not count it toward the sum. But if it is odd, then I have to use it to get the sum. So what I'm going to do is I'm going to have basically a similar for loop. I'm going to translate this for loop to MIPS. Sum is 0. That's a declaration first. That's going to eventually contain my output. Then I'm going to have a for loop for I from 1, I less than or equal to n I++. That's the same exact for loop I had in the previous experiment. Then here I will say if I and 1 is equal 1, then sum plus equal I. So what does this mean? I and 1, this is the bitwise AND between I and 1. That's going to mask all the bits except the rightmost bit. When you write a number in binary, if the rightmost bit is 1, the number is odd. If the rightmost bit is 0, the number is even. That's very simple way of finding the remainder of a number when it's divided by 2, so that you can find out the parity of number. Is it even? Is it odd? If I and 1 is 1, the number is odd. So we're going to count it toward the sum because that's what the question says. Otherwise, if I and 1 is 0, then we're going to skip that. We're not going to do the sum plus equal I statement, and we're going to go to the next iteration of the for loop. There are better ways to do this calculation, I'm sure, but the reason I did it this way is because I'm going to show you how the if statements can be converted to MIPS. So this is just for illustration purposes, nothing efficient here. I don't want to say this is an efficient way of finding sum of odd numbers from 1 to n, but this is just an example. So let's uncomment this part. I'm going to first do the same thing I did before, initializing sum to 0. Then I'm going to say, let's set I equal to 1, beginning of the for loop. I call my for loop for 2 because that's a different for loop. So I just wanted to distinguish this for loop from the for loop of the previous example. Then I'm going to compare n with I. If n is less than I, or if I is greater than n, we are done. We should jump to exit 2. That's the end of this code. And then otherwise, we're going to do the body of the for loop. The body of the for loop is an if statement. So I need to do this if statement. In order to do this if statement, I'm going to first bitwise and I and 1. How do I do that? I will say and I which was in S1, 1, do the bitwise and store the result in T1. If T1 is 0, that means the number is even. That means the bitwise, that means the remainder of number when divided by 2 is going to be 0. So jump to inc2. Inc2 is going to increment I, and it's going to jump to the beginning of the for loop. So we're going to go to the next iteration, basically, because if I is 0, we should continue the next iteration. If I is even. If I is odd, we do not jump in this line, and we do not jump to the line inc2. And instead, we're going to do this one first, which means updating sum. Sum is going to be added by I. Then I'm going to do I++. Then I'm going to jump to the for loop beginning, which is here. So that's basically how this is written. Let me save this. Let me update the output statement. I'm gonna uncomment result 8, which basically prints some of odd numbers from 1 to n. And let's go to the same browser, browse the same file, and then press play. Number is 10. You should expect 25, I guess. Yes. So numbers from 1 to 10 was 55, but if you only count odd numbers, then it would be 1 plus 3 plus 5 plus 7 plus 9, which you can just do a quick math and get to the number 25. To do the next one, the next experiment would be similar to the current experiment, but we're going to do a sum of even numbers. So let's comment this and uncomment this. All right. The next experiment says find the sum of even numbers from 1 to n. So it's going to be the same code with a small difference. The difference is the remainder of dividing I by 2 should be 0 here. If it's 1, we should not add I by some, but if it is 0, we should do that. How to get the remainder of I when it's divided by 2? We just simply do a bitwise and by 1. And if it's 0, we're going to add I by some and store the result in sum. So the code is exactly the same as the previous experiment. The only difference is instead of saying BQ T10 inc, we do BNE T10 inc, which means if it's even, jump over the sum plus equal I statement, immediately increment I by 1 and jump to the beginning of the for loop. As you see, I call this for loop label for 3. And then here I have exit 3, but the reason I did this is because I wanted to get like different labels from the previous code. So I didn't want to reuse the same label. All right, so after doing this, let me do a little bit of manipulation on my output statement and print some of even numbers from 1 to whatever n is equal to the result. Let's go back, browse the same ASM and press play. It says, what's your input? I will say 10, and then it's going to do the calculation and comes up with 30. because the answer to the two previous experiments was 55 and 25. When you subtract them, you get to 30, and that's basically reasonable because the sum of even numbers plus the sum of odd numbers from 1 to 10 should be the sum of all numbers from 1 to 10, because every number is either even or odd. So this is perfectly correct. I have two more experiments, which I'm going to do this pretty quickly. All right, the next experiment is dividing n by 4, or getting a quarter of a given input, right? And is the input given or finding a quarter of that, or dividing n by 4. Of course, this is an integer division, which means if there is any remainder, we're going to skip that. We're going to only get the quotient of dividing n by 4. And that's a quarter of n, whatever n is. If n is 20, the answer is 5. If n is 10, the answer is 2. If n is 5, the answer is 1. If n is 100, the answer is 25. And instead of dividing, which is a very time-consuming operation in MIPS, we're going to do a much simpler instruction, and that's shift right logical. When you want to divide by a power of 2, in this case 2 squared, all you need to do is shift 2 bits to the right. That's how this operation can be done. Shifting to the right basically means move all the bits to the right by a number of steps. And this way, if you have, let's say, shift to the right by 2 bits, the last 2 bits will be dropped. The last 2 bits are going to be the remainder of dividing by 4 or dividing by 2 squared. And then 2 new bits will be added to the left side. The 2 new bits are going to be zeros. Long story short, shift right logical is equivalent to dividing by power of 2. In this case, shift right logical S0 and 2 is going to divide them by 2 squared, which is 4, and then it's going to store the result in a 7. Let's see if that's what we expect. Let me browse the code and play. Let's say n is 10. The answer is 2. Let me reset this and try again. You can reset it and play again, because you can just try it for different inputs. This time I'm going to put 20, and the output should be 5, because 20 over 4 is 5. Let's reset it, play again. Let's put 100, and the answer should be 25, because a quarter of 100 is 25. So that's pretty much what we expected. Let's get prepared for the last experiment. All right, so the last experiment is this. It's shift left logical, and the shift left logical is kind of similar to shift right logical, but it's just shifting it in the other direction. And when you shift it in the other direction, it's like multiplying the number by a power of 2. So if I want to, let's say, multiply my number n by 8, which is a 2 cube, I have to shift it to the left by 3 bits, because 8 is 2 to the power of 3. So this is what I do: shift left logical, S0 and 3, and I'm going to store the result in S7. At the end, I'm going to print the output. So let's see if this is going to print 8 times whatever input is. Let's uncomment this. That's result 11. It says 8 times, right? So let's go back to the browser, browse the new values for the file example.asm, and press play. Let's say input is 10. 8 times 10 should be 80, which is basically the case. If I, let's say, reset it and play again, and n is negative 12. Negative 12 times 8 is going to be negative 90. I should say 96, right? Correct. So that's going to give you the output. Although this input says should be non-negative, but if you put non-negative in some cases, if you put negative in some cases, it's going to work. So you can play with this. I'm going to give you access to both the code and also this website's URL. Thank you for watching.